In the previous class, we saw some examples of how to calculate concentration in different units and also looked at how they can be interconverted across these units. In addition, we also tried to understand a little bit of how equilibrium constant can be determined for the same reaction in non-stoichiometric amounts and when they don't go to completion. In today's class, we will be looking at some examples of acid-base equilibria. We had already defined a few parameters. Let me redefine them so that we get the class started. We defined pH as minus a logarithm of the concentration of H3O plus ions, and this is for strong acids. On the other hand, for weak acids, we were able to derive the Henderson-Hasselbalch equation that goes as pH equal to pKa minus log of A minus by HA. Weak acid. The other parameter that can be defined, of course, here it was defined with a parameter called Ka, which is the equilibrium constant, the acidity equilibrium constant. Similarly, one can also define the basicity equilibrium constant. Let us say you have B, which is a weak base that abstracts a proton from water. It is defined by Kb. So, why don't we write the Kb? So, let us take a similar example as we had taken earlier. For instance, let us say you have A minus plus H2O giving Ha plus OH minus. So, similar to the acidity constant that you have seen before. So, we are talking about Ka and Kb for the same chemical. So, in which case what ends up happening, Kb can be given as, activity of Ha times activity of OH minus divided by activity of A minus activity of H2O. We know that activity of H2O is 1, so we are not going to write it any further. And we define what is activity. Activity goes as the mole fraction or the concentration depending upon the solute. So, let us assume that this is at a low concentration, which will end us approximating the activity to the concentration of the solute itself. So, this ends up becoming Ha times OH minus divided by A minus. And how was Ka defined from this equation? Ka was defined as H3O plus times A minus divided by Ha. Of course, here also we assumed the activity of water is 1 because it is a pure state, and we approximated activity to concentrations. So, one is able to realize if you take a product of Ka times Kb, what ends up happening is that in the Ha terms will start to cancel and the A minus term starts to cancel, and you are going to be ending up with H3O plus times OH minus. This is nothing but Kw. So, for a given chemical, the product of Ka times its Kb is equal to Kw. Okay. So, let me also write the equation here, Henderson-Hasselbalch. And of course, we know that Kw is 1 into 10 power minus 14 at 25 degrees Celsius. Okay, now that we have seen it, let us take some examples. What is the pH of 30 millimolar NaOH? As we are able to realize, pOH is like a definition of pH, which is given as negative logarithm of OH minus ions. Simple math and our intuition clearly says pH plus pOH will be equal to pKw, which is nothing but 14. So, now we know that for NaOH, it's going to completely dissociate at this concentration to give Na plus and OH minus ions. So, if you had 30 millimolar of NaOH, you are going to have 30 millimolar of hydroxyl ion. So, therefore, the POH is going to be given by minus log of 30 times 10 power minus 3 since it is milli. So, this will translate itself to something like 3 10 power minus 2. This is going to be 2 minus of log 3, which is 0.4771. So, that will be equal to 1.53 in POH. Therefore, the pH for this solution is going to be given by 14 minus 1.53, that is going to end up becoming approximately 12.47 units. What we are able to see here is for a given acid or a base, you can define the pH that is associated with it. Let us try to see what happens when we mix acid and bases together. We are very well aware of the fact if you mix strong acid with strong base, you get a neutral salt and water that comes off it. Let us take such an example. Let us say we have 2 ml of HCl at pH 3, and then to this you are adding 4 ml of NaOH at pH, let us say at 10. So, this immediately implies then let us say you add these things together, you get 6 ml of solution. What is the pH? Let us try to answer this question. So, let us take it stepwise. When you are trying to say concentration of HCl at pH 3 is going to be pH equal to 3, assuming full dissociation, this is going to be minus log of H3O plus ions in solution 1. So, I am going to call this solution 1 and this solution 2. So, this is going to imply H3O plus is given by 10 to the power of minus 3 molar, and you have 2 ml of it. So, therefore, the number of millimoles, so H3O plus concentration is going to be given by 10 to the power of minus 3 moles times 2 ml, which is going to be 2 into 10 to the power of minus 3 millimoles. Okay. So, this is the amount of H plus that you have in your hand, and let us determine what is the concentration of OH minus that is present, that will end up neutralizing this acid. At pH 10, we understand that the POH is 4 units. If the POH is 4 units, this implies minus log of OH minus is this, which will end up as 10 power minus 4 molar NaOH is present. So, if 10 power minus 4 is present, how many millimoles of OH minus is present? That is going to be 4 times 10 to the power minus 4 millimoles. Of course, I am writing millimoles because you are using milliliter here. So, this can be rewritten as 2 micromoles. So, now you have a given amount of H3O plus and given amount of OH minus ions that are present. Okay. So, this could be written as 4 into 10 to the power of minus 7 moles, which is 0.4 micromoles. So, you are able to realize that you have more amount of H plus ions than the OH minus ions. So, basically the resultant solution should be acidic. So, when you are neutralizing these two, what ends up happening, you are going to have 0.4 micromoles of H plus neutralized by this 0.4 micromoles of OH minus. So, finally, what ends up happening, the amount of H3O plus that is going to be present is going to be 2 minus 0.4 micromoles, that is going to end up as 1.6 micromoles. Of course, this can be rewritten as 1.6 10 to the power of minus 3 millimoles. Remember, we have to convert it back into concentration, which is in molarity. So, therefore, what is going to end up happening, how much ml. So you are having 6 ml that is going to be present. So molarity is equal to number of moles by the total volume that you have in, of course, liters. So you have something as 1.6 10 to the power of minus 6 moles divided by 6 ml. So that is going to be equal to so therefore the pH is going to be given by minus log of 0.267 times 10 power minus 3. This is going to be 3 minus log of 0.26. This is going to be equal to 3.57 units. So basically what you are able to realize is that by addition of H plus and NaOH, and with the NaOH concentration being a little lower, you are able to realize you are pushing the pH from 3 to 3.57. This example shows that what happens when you add a strong acid and strong base at given concentrations. Let's try to ask the same question but in a slightly different way. We just defined that the pH is given by minus logarithm of H3O plus for strong acids. Let's say you have 1 millimolar of HCl, immediately you are able to say the pH is 3, as we just saw in the previous example. But let's say if you are using a concentration of strong acid that is similar or less than that of 10 power minus 7. So let's take an example. What is the pH when you have a 10 power minus 7 molar HCl? It is very tempting to say the pH of this solution is 7. To obscure this point, let's say you have a 10 power minus 8 molar HCl, it's very tempting to say the pH is 8, but this is not correct. So is this. You are able to realize that if you are going to add a concentrated acid, the pH has to be less than the neutral pH, and at 25 the neutral pH is 7, so therefore it has to be less than 7 units. So where are we going wrong? Let's take this problem stepwise. HCl at this concentration can be very well approximated to be completely dissociated to hydronium ions in the presence of water and chloride ions, and water of course undergoes self dissociation into hydronium ions and hydroxyl ions. So therefore the total concentration of hydronium ion in such a case is going to be given as a sum of the concentration of the chloride ion and that of the hydroxyl ion that comes from water's self dissociation. So when you are having this case, we just took an example of 10 power minus 7 molar. So you are able to realize this is going to be 1 into 10 power minus 7, and the OH minus we know for a fact is given by Kw divided by the H3O plus ion concentration. So doing the basic LCM, you are going to get H3O plus the whole square minus 10 to the power minus 7 H3O plus minus Kw. I am going to write it directly as 1 into 10 to the power of minus 14 is equal to 0. So this is a quadratic equation which we can solve by trying to find the solution H3O plus minus B. So it's going to be plus 10 power minus 7 plus minus square root of B square. So that makes it 10 power minus 14 minus 4 times AC, minus of minus becomes plus 10 to the power of minus 14 divided by 2A. So this, let's with quick arithmetic, square root of 5 is 2.236. This will be, you have two solutions here, you have a plus or a minus, and you realize that the minus 2.236 results in negative concentration of hydronium ions, which is not possible. So therefore we are only going to take the solution where you have the plus. So therefore this is going to end up as 3.236 into 10 to the power of minus 7, of course divided by 2. So this is going to be 1.618 10 to the power of minus 7 molar. So now the pH of 10 to the power of minus 7 HCl solution is going to be given by minus log of 1.618 in 10 to the power of minus 7. This is going to be 7 minus log of 1.618, that is going to be equal to 6.7 units. So you realize that although it is very tempting to say the pH of 10 power minus 7 molar HCl is 7, it is actually wrong. It has to be less than 7, and you do see it is a little less than 7, which is at 6.7. So be very careful when answering such questions. So let us solve one more question to finish up the entire discussion. So let us say we have to calculate pH of a solution that has initial acetic acid concentration at 10 millimolar. So what is the pH of a 10 millimolar solution of acetic acid? Of course, we are assuming it is all 25 degrees. The equilibrium experiments, you have to mention the pH and the temperature at which it is being performed. So if we do not say anything in the assignment or in the tutorials, it immediately means that you are assuming 25 degrees Celsius. So acetic acid is a weak acid, and we realize that it is not going to completely dissociate to form acetate anion and the hydronium ion. So 10 millimolar can be written as 10 to the power of minus 2, and let us say you started with 0, and then let us say there is a certain amount of conversion, let us assume that as x. So you are going to have Ka that is going to be given by, assuming at low concentrations you can approximate activity to the concentrations. This is going to end up as x square divided by 10 to the power of minus 2 minus x. So now if we know the Ka of acetic acid, we should be able to determine what is indeed the pH. So let us quickly calculate that. It is given that Ka of acetic acid is 1.75 in 10 to the power of minus 5 units. So this is going to be equal to 1.75. Okay. So now that is done, let us determine what is x. So this is rearranging, quick rearranging gives us, therefore x is going to be given by, why are we trying to determine x? Because x determines what is the pH of this solution. So this is going to end up to be once again, we are only going to take the plus solution, not the minus solution. So what we are able to realize here is that if you take a weak acid, so although we are taking 10 power minus 2 molar, you finally end up with a pH of 3.09. You finally end up with a pH of 3.1 units. Had you taken a strong acid, you would have been at a pH of 2. So this clearly indicates the degree of dissociation. It's given by the parameter Ka, makes you understand why pH of weak acids would end up to be little lower at a given concentration against a strong acid.